Hello everyone, welcome to day 16 of Advent of Code. Today was another easy day. Part 1 was just a basic optic simulation for us to code up, and while it was intricate, there were no gotchas or tricks that we had to find. Then, Part 2 was just to run Part 1 n times. Hardly interesting. What was interesting, however, was the visualization we created. It's certainly the most intricate SVG we've had to generate so far in Advent of Code, and it pushed us to the limit of what we can do just by writing XML manually. Next time, we'll have to do something more sophisticated. As always, this video has chapters so that you can skip around, and the link to the code is in the description below. Now, without further ado, let's get started. Day 16. The floor will be lava. With the beam of light completely focused somewhere, the reindeer leads you deeper still into the lava production facility. At some point, you realize that the steel facility walls have been replaced with cave, and that the doorways are just cave, and the floor is cave, and you're pretty sure this is actually just a giant cave. I feel like the reindeer is leading us into the big magma chamber in the middle of Mount Doom, and then they're going to chuck us in, like Frodo did the One Ring. Finally, as you approach what must be the heart of the mountain, you see a bright light in a cavern up ahead. There you discover that the beam of light you so carefully focused is emerging from the cavern wall closest to the facility, pouring all of its energy into a contraption on the opposite side. The beam of light they keep referring to is yesterday's problem, where we basically built a laser by executing a simple algorithm and slotting lenses into boxes. Upon closer inspection, the contraption appears to be a flat, two-dimensional square grid containing empty spaces, mirrors, and splitters. The contraption is aligned so that most of the beam bounces around the grid, but each tile on the grid converts some of the beam's energy into heat to melt the rock in the cavern. You note the layout of the contraption, your puzzle input, for example. So it's a grid of dots, pipes, dashes, and slashes and backslashes. The beam enters in the top left corner from the left and heading to the right, then its behavior depends on what it encounters as it moves. So top left corner, so it goes this way. If the beam encounters an empty space, a dot, it continues in the same direction. If the beam encounters a mirror, a slash or a backslash, the beam is reflected 90 degrees depending on the angle of the mirror. For instance, a rightward moving beam that encounters a slash mirror would continue upward in the mirror's column, while the rightward moving beam that encounters a backslash mirror would continue downward from the mirror's column. So this is pretty much the obvious movement. If the beam encounters the pointy end of a splitter, a bar or a dash, the beam passes through the splitter as if it were empty space. For instance, a rightward moving beam that encounters a dash splitter would continue in the same direction, and presumably a downward moving beam that encounters a pipe would continue moving in that direction. If the beam encounters the flat side of a splitter, a pipe or a slash, the beam is split into two beams going in each of the two directions the splitter's pointy ends are pointing. For example, a rightward moving beam that encounters a pipe splitter would split into two beams, one that continues upward from the splitter's column, one that continues downward from the splitter's column. Beams do not interact with other beams. A tile can have many beams passing through it at the same time. A tile is energized if that tile has at least one beam passing through it, reflect in it, or split in it. In the above example, here is how the beam of light bounces around the contraption. So the beam starts from the left and goes into the splitter. Then it splits upward, but that's the wall of the cave, and then also downward. It then hits this splitter, and then it splits it left and right. When it goes left, it eventually hits the wall of the cave, and when it goes right, it hits this 45-degree mirror, which throws it upward presumably. And from here, it throws it to the right. From here to the bottom, then it hits this splitter here. And then it goes to the left, gets split here, which then goes back into the top splitter, which we've already been through, and then it also goes downward, hitting the wall of the cave. This splitter also goes downward and hits the wall of the cave. What's this 2 here? Oh, actually, the split earlier went to here and then went through here. Then also went up and through this mirror and then through the splitter above. Then through this splitter as well. This splitter sends a second a second beam of light downward. But why did this beam of light not get... Oh, and then it goes through the pointy edge of this splitter, so it doesn't get split into two sides. But then we also have a beam of light going upward, then left, and hitting this splitter, which is the original splitter. So this is a bit like a graph traversal, except we have cycles. I mean, not except, it's a graph traversal with cycles. Beams are only shown on empty tiles. Arrows indicate the direction of the beams. If a tile contains beams moving in multiple directions, the number of distinct directions is shown instead. Here is the same diagram, but only showing whether a tile is energized or not. Ultimately, in this example, 46 tiles become energized. The light isn't energizing enough tiles to produce lava. To debug the contraption, you need to start by analyzing the current situation. With the beam starting in the top left heading right, how many tiles end up being energized? So the question is, can we just follow the algorithm and iterate through this grid? The answer to that is whether our puzzle input is too big. And it's not. We can definitely just traverse this graph. I do note that a lot of the spaces seem to be empty. There's probably some optimization to be done with what can be reached from where. Okay, so here's the plan. We're going to parse our input. Then we're going to store it as a map of coordinate to character in the coordinate. If there's nothing in the map for a coordinate, that means it's an empty space. We are then going to walk this graph and just keep track of the things we've visited. And that's it. No, that's not it. Because we also need to the actual question is how many tiles become energized. So we'll somehow need to keep track of how many empty spaces we've traversed. But I think we can just do that whilst walking the graph. As in, say we're here, and now we know that we have to go up and down. If we go up, then we just hit a wall, so we're done. If we go down, we search the graph, we search our map for these coordinates, and we find that they are empty. And every time they're empty, we increment our number of energized tiles by 1. Then we hit this one, and now we can actually find something in our map, so we look up the values there, then we keep on going. And then when we later reach this splitter from the left-hand side, from the right going left, we reach this splitter. And then when we go down here, well, we've already visited this splitter before, so we know that it doesn't count as energized. So we stop traversing, so we don't add any more energized tiles to our pile. Okay, I think this is doable. We can also do a bit of drawing to illustrate what this actually looks like. Yes, so we're not just going to store the count of energized tiles, we're going to also store their coordinates so that we can draw them out nicely. Then we can debug what's going on. Let's get started. So here, when we do the parsing, we are we first iterate over every line and then every character in the line. Then we are going to output the coordinates and then an atom to describe what we're seeing. So if we have a pipe, we see split vertical. Now here we go, we have our map that associates our coordinates with something describing what is at that coordinate. And we have nothing for the empty spaces. Let's move this into a module and let's make a little visualization for it, since this particular map is sort of unreadable. So this bit of code generates some SVG. Fundamentally, all it does is it generates an SVG string using the HEX templating language. Then it pipes this into Keynote Shorts HTML, which just displays a raw HTML. And our raw HTML happens to just be an SVG and nothing else. We are now going to use this to draw our maze. This. Draw now takes maze as an input. We can do this slightly better here. When we read our input, we don't just, we are going to call this room. Then we are going to return a map from room to room. Doing it like this is very useful because it allows us to later add more pieces of data to this data structure. But then we can have just this one data structure that we pass to all of the functions, then we just add or remove elements to this as we need. With our visualization out of the way, let's actually do the traversal. We start in the top left corner and we're going right. Then we have to actually simulate hitting this, going down, so on. And while we do this, we'll also keep track of which squares we visited and which have been energized. And in fact, we just need to keep track of which squares have been energized because those will also be our visited squares. Okay, this did a bunch of stuff, and now we have something in visited. So next up, let's draw what we have in visited. Comment this out. Here. So we now have a visited to draw. Alright, now we can actually debug why this doesn't work. Because here, it should have gone up, but it didn't. Why did it not go up? So this is a left up mirror, LU. Or in the LU case, oh, it did not go up because we did not implement it. Fine. Bam! It drew a bunch more stuff. Does it look like what Date said it should look like? Here we go. So we've got lines going down here, arrows going down here, arrows going left there. Arrows going left, then we've got both up and down here. Both up and down, yeah. Then there's the 2 here because 2 arrows are overlapping, a 2 here. Got a bit to the side and 2 down. A bit to the side and 2 down. Okay. So I claim that if we count all of these things, if we count all of the energized cells, all of the visited cells, we should get the number they asked us. Right? Right. But perhaps draw these lines slightly differently. Basically, every one of these triangles would be better drawn as 2 triangles, one a bit above and one a bit below. Then if we have crossing triangles, we'll do that later. Let's actually see that we solved part 1. So we have propagated the beam here. We have visited somewhere. Do have visited, right? We have visited. So now we just need to turn this into a list, get the tuples, and deduplicate and count. So app fn pause there, we just want the position. Sort dupe and num count. 46. 46 tiles become energized. Alright, let's now do this for the full. 8125. 125. That's the right answer. You are 1 gold star closer to restoring snow operations. Okay, so what do we do next? Next, we can either look at part 2 or we can make our visualization better. Let's look at part 2 first and then we can think about the visualization. So, part 2. As you try to work out what might be wrong, the reindeer tugs on your shirt and leads you to a nearby control panel. There, a collection of buttons lets you align the contraption so that the beam enters from any edge tile and heading away from that edge. You can choose either of the 2 directions for the beam if it starts on a corner. For instance, if the beam starts in the bottom right corner, it can start heading left or upward. So the beam could start on any tile in the top row heading downward, any tile in the bottom row heading upward, any tile in the leftmost column heading right, or any tile in the rightmost column heading left. To produce lava, you need to find the configuration that energizes as many tiles as possible. This is looking like we can just brute force it. In the above example, this can be achieved by starting the beam in the fourth tile from the left in the top row. Fourth tile from the left in the top row. Here. So it's saying we start here and then go down. Using this configuration, 51 tiles are energized. We'll take their word for it and we're going to draw it out. Find the initial beam configuration that energizes the largest number of tiles. How many tiles are energized in that configuration? Okay, we are just going to brute force this. This is... yes, so we can just brute force this. Let's look a bit at the complexity of our algorithm. So this is our board. We are basically doing a graph traversal across the board, which means, but we never visit a cell more than once. Or in fact, we never visit a cell more than 4 times, because each cell can have a beam of light traveling through it 4 times. But 4 is a constant, so we only visit every cell a constant number of times at most. So our base algorithm is quadratic, or it's linear in the number of cells in the grid, which we're just going to call quadratic since n is usually taken to be the side of this grid. So in order to brute force their algorithm, we have to try starting our beam from every possible edge, every possible cell on the edge. And that's 4 times the side, so it's a constant times the side, so this is another n. So our whole algorithm, which is trying to energize from all of the edge cells, is going to be cubic. And cubic is fine for the size of the grid they gave us. Or so I claim. But we're going to find this out very quickly because we're just going to write it, and it won't take long at all. So let's create a new section. Let's call it part 2. Now, we basically do the thing from the first. Yeah, we basically do the thing from the first part, except we call the more advanced propagate beam. Here. The arity 2 propagate beam lets us specify the starting position. And we now have to try many starting positions. And now here we just need a num.max, which is 51. Now if we do this on the full example, it should work. It's a cubic algorithm, so it takes a while. Probably should have made it print out something so that we see how far along it's gone. But it gave us an answer, 8489, which is indeed bigger than 8125. So 8489. That's the right answer. You are 1 gold star closer to restoring snow operations. You have completed day 16. Alright, so we're done. Except that we want to make the visualization better. And oh wow, this looks... Right, we have completed day 16, so now the volcano is online. And now I see how the path here goes. We started off in the submarine, got launched on a trebuchet, went up a gondola to a floating island, then took some boats, then went to Volcano Island, fixed the volcano, and now presumably we're going to go here and fix the factory that uses the lava from the volcano to make machine parts for the sand machine that is here somewhere. And then we're going to go all the way back. So presumably our ending position is here. Right? Yeah. So we've been doing this. We end back where we started. Okay, but before that, let's look at day 16 again. Oh, let's make our visualization nicer. So our visualizations here should still run, yes. But I would like to make it prettier. And now we should be done with our triangles. Does this make sense? So beam of light goes through here, then it goes down, splits the side, and then here. It goes up, up, follows down, then splits here in two directions. One direction goes like this, which is up and down. The other direction goes down. No, where was it? Here. And then it goes here, which goes down and up, goes up, splits, then goes back into here. Okay, this looks nice. I think this is readable. The thing is that if I try to draw this on the big one, it's going to look terrible, isn't it? What happens if we try to draw full like this? This looks less terrible than I thought it would. You can actually kind of see the patterns. Huh. This is surprisingly nice. Sort of artistic with all of the dots. Yeah, we're going to leave it like this, and this is going to be the thumbnail. Alright. So that's it for the visualization. Can we refactor anything here? We can refactor some of this logic, but honestly it's not worth it given that it only repeats twice like this. The parsing is already shared, so there is really nothing to refactor here. So, review time. Today was fairly easy, we just had to implement an algorithm. The algorithm involved walking along a grid, and it was somewhat intricate to actually code up, but nothing really tricky or challenging. And then for part 2, we just brute forced it. There's probably some memoization that can be done here, but again, doesn't really seem worth it given the size of the problem. And then we drew a visualization to actually show what we're doing. And here it is. How are the stats looking for today? How are the stats looking in general, rather? So, about the usual number of people have solved today. Yeah, and then the only day that's really an outlier is day 12. People just gave up on that, which is unsurprising given how annoying it was. Okay. Oh, and notably, almost everybody who solves part 1 solves part 2, more or less, because indeed, you can just brute force part 2 using part 1. So that's it for today. Thank you for tuning in, and see you tomorrow when we do day 17.